Edwin James George Pitman was born of English parents in Melbourne, Australia on 29 October 1897. He was educated at South Melbourne College and later studied mathematics and physics at the University of Melbourne. He graduated with a BA in 1921 after military service with the 14th Battalion of the Australian Infantry Force in 1918-19. He was appointed acting professor of mathematics at Canterbury College, University of New Zealand in 1922 and returned to Melbourne in 1924 to become tutor in mathematics and physics at Ormond and Trinity Colleges and part-time lecturer in physics at the university. He became professor of mathematics at the University of Tasmania in 1926, a position which he held for 37 years before retiring at the end of 1962. Professor Pitman travelled to the United States for the first time as a visiting professor in 1948-49, when he lectured at Columbia, North Carolina, and Princeton. He returned to Stanford in 1957, Johns Hopkins in 1963, and Chicago in 1968-69. He was a visiting senior research fellow at the University of Dundee, Scotland, in 1973. He has been closely involved in the development of mathematics and statistics in Australia. He was president of the Australian Mathematical Society in 1958-59 and became an honorary life member in 1968. He was made an honorary life member of the Statistical Society of Australia in 1966. The Statistical Society's highest honour, the Gold Pitman Medal, was named after him. He was presented with the first medal in 1978. Among his other honours are Fellowship of the Australian Academy of Science in 1954, membership of the International Statistical Institute in 1956, and honorary fellowship of the Royal Statistical Society in 1965. He has also been awarded an honorary DSc by the University of Tasmania in 1977. It is a pleasure and privilege on behalf of the Statistical Society of Australia and the Australian National University to introduce Professor Pitman, who will give Reminiscences of a Mathematician who strayed into statistics.
I remember very clearly my first encounter with statistics at the age of 23 in a course called Advanced Logic at the University of Melbourne, given by Professor W.R. Boyce Gibson, a well-known and very able philosopher and an excellent lecturer. He devoted 2 or 3 lectures to the subject of statistics. I decided then and there that statistics was the sort of thing I wouldn't have to bother about, and that it would never interest me. 4 years later, in 1925, I applied for the professorship of the University of Tasmania. Applicants were asked to state whether they had any knowledge of statistics and if they would be prepared to teach a course in the subject. I wanted the appointment, so in my application I wrote, "I cannot claim to have any special knowledge of the theory of statistics, but if appointed, I would be prepared to lecture on this subject in 1927. I now think that the word special could have been deleted with accuracy, but I was being careful not to exaggerate. My application was successful, and so I was committed to teaching statistics, and therefore, in spite of my youthful aversion to the subject, I was committed to learning it. It happened that I was also very soon involved in applying it. In fact, I began almost simultaneously the 3 activities of learning, teaching, and applying statistical theory. I learnt much of the basic theory of statistics from George Darmois' excellent little book, Statistique Mathématique, published in 1928. And according to the 14-page critically commending preface written by Monsieur Hubert, the director of the statistical office in France, It was the first important French work on modern statistical theory. Borel's many-volume treatise on probability was being published, and that was a help. Sometime about 1928, a part-time student of mathematics, R.A. Scott, who worked in the State Department of Agriculture, brought me one day the data and statistical analysis of some NPK field trials on potatoes, which he asked me to comment on before he sent them for final criticism to Dr. John Wishart at Cambridge. He also produced, open at the appropriate page, Fisher's Statistical Methods for Research Workers, which I had not seen or heard of. I took the papers and the book home. After studying them that night, I decided by the light of common sense that the calculations were sensible and according to Fisher. And I reported next morning that as far as I could see, everything was correct. This was confirmed later by Wishart. That was my introduction to Fisher, and in particular to the analysis of variance. It was also the beginning of a collaboration with Scott and the Department of Agriculture in field trials. I very soon began to wonder about the validity of applying normal theory to our randomized blocks and Latin squares. One can go a long way in the analysis of variance without invoking the normal genie. It's only when you consider power functions and significant tests that the actual distribution comes in. These wonderings led me later on into what are now called non-parametric statistics. But an immediate result was the invention of the semi-Latin square, an arrangement of 2n treatments applied to 2n squared plots arranged in 2n rows and n columns. Others may have used the design before or since, but I'm quite certain that inadvertently I named it. In planning experiments, I said to Scott one day, this is a design I'd like to try. It's a sort of semi-Latin square. This is the sort of thing with n columns, 2n rows, and 2n treatments, and 2n squared plots. A generalization, which is what we actually used, replaces the 2 by m. That is to say, you get n columns, mn rows, and n blocks of m rows each. I called it a semi-Latin square. A better name would have been a partial Latin square, or as they now call it, I think, the modified Latin square. I had two reasons for evolving it. The first was that our Latin squares in the field were not squares. They were long rectangles. That's because they were much longer than this, because the plots were not squares, but long rectangles, rows of potatoes. So that we had a Latin square which was spread out like that. I thought that the effect of variation in fertility would be better allowed for if we had the whole area square. That was why I got double the number of rows, which were narrow, and the same number of columns. The other idea that was in my mind, it was not a standard design, and but with the usual assumptions of independent residuals with zero means and common variance, the ordinary analysis should be valid. I wanted to get the reaction of the statistical establishment in order to find out what model they really used. The design was first approved by Fisher, who said that Student had used it, and by Wishart. Later, it was condemned by Yates and Fisher on the ground that with the usual analysis it gave a biased estimate of error. They were evidently using a different model, and my suspicions were confirmed. I started to study statistics in 1926, and I did not publish anything until 1936. There were two main reasons for the delay in publication: the workload I had to carry and the nature of my upbringing. When I went there in 1926, the University of Tasmania was a very small university which was just beginning to grow. The Department of Mathematics consisted of myself and a part-time lecturer. By 1948 it had grown to a professor, an associate professor, 2 lecturers and 2 tutors, and now it's a very large department. I had to teach a wide range of mathematics, pure and applied. For many years I gave 12 lectures a week, and we worked on Saturday mornings. Let me say that at the time I did not think that that was abnormal. As a student, I had had 3 years of university mathematics, interrupted by 2 years in the army, and followed by a year of mainly physics. In those days there were no graduate schools of mathematics in Australian universities. Some of the other universities had scholarships which enabled promising young mathematicians to go abroad for further study, mostly to Cambridge, England. When I left the University of Melbourne, after 4 years of study there, I had had no training in research, but I thought that I had learned to study and use mathematics, and that I would be willing to tackle any problem that arose, even if that necessitated learning a new branch of mathematics. I regarded myself as a general practitioner, with most of my learning still to be done, and not as a specialist. The lack of research training was a handicap, which took me some time to overcome. One result was that for many years I never gave a thought to printed publication. What eventually spurred me to publish was a government research grant to the university. In 1936, the Commonwealth Government decided to provide £30,000 a year for a period of 5 years for the promotion of scientific research in the university. On a state population basis, Tasmania's share of this would have been 1/30th, but we were allocated more than double this, 2,400. That was the beginning of the entry of the Commonwealth into education. Under the Australian Commonwealth Constitution, education was the affair of the states and not the Commonwealth. But later on, sometime after 1936, the Constitution was amended to allow the Commonwealth to do all the things it does in education now. But this was the first thing that it did. At that time I was chairman of the professorial board and had had prior knowledge of what the Commonwealth government was about to do. I was determined that when we presented our first annual report, we should have more than progress and promises to write about. The only satisfactory report is published papers. So I immediately set to work to write my first paper for publication. My first try was on a topic in hydrodynamics, but when I had typed it out, I didn't think it was worth publication, so I had to think of something else. For some time I had already been teaching. I'd already obtained the general form of distributions which admitting sufficient statistics. With this as a start, I wrote a paper entitled Sufficient Statistics and Intrinsic Accuracy. I sent the paper to Dr. John Wishart of Cambridge University. I had had no direct contact with him, but I thought he would know my name from my connection with the Department of Agriculture's field trials, results of which had always been sent to him for comment. He reacted magnificently. He wrote back warmly welcoming me as a mathematician interested in statistics, and said that the paper would be published in the Proceedings of the Cambridge Philosophical Society. Not only did he arrange for the publication of that paper and the 7 other papers that I wrote in the next 2 years, but he also did all the proof correcting of all the papers. I sent them off and they came back printed. I met Wishart only once in 1949 at dinner in Sam Wilkes's house at Princeton. It gave me the opportunity to express in person what until then I had been able to do only by letter. my great gratitude for his marvellous kindness in helping me at a critical stage. I was surprised to find that he was a voluble talker. Soon after dinner, Wilkes's son turned on the television in a distant corner of the large room in which we were sitting. Television was then very new. Gradually the guests drifted over to the TV set and conversation ceased. Most of the program was an old Charlie Chaplin film which was obliterated whenever an aircraft flew overhead. At the end of the evening, I left with Wishart and somebody else. When we got outside, Wishart exploded. He had been bottled up most of the evening and felt he had been suppressed. That was the last I saw of him. He was drowned later that year. It was lucky for me that by the time I started to write, air mail services had started. The combination of that and Wishart's assistance made publication very quick, a most encouraging thing for a beginner. One of my papers, the second I think, was carried in an aircraft which came down in the sea. The mail was salvaged and my paper arrived at Cambridge wet through, but still legible after drying. When I started to study it, statistical theory was dominated by the normal distribution. Most of the statistical tests in common use were based on the assumption that the distributions sampled were normal, and that worried me. For example, the t-test for the significance of difference of means of two samples assumes that the distributions are normal with the same variance. We can devise a corresponding test for samples from two continuous distributions of any given form, which differ only in location. But what can we do without making any assumptions about the specific form of the distributions? Well, supposing we have two samples, x1, xm, mean x bar, and y1, yn, mean y bar, and wish to test the hypothesis that the distributions sampled are the same against the alternative that they differ only in location. Well, if the two distributions are the same, we could do an equivalent operation by taking a sample of m plus n from a distribution of that type and then dividing it into a sample of m and a sample of n by some method which makes all such separations equally probable. If we then compare the observed value of x bar minus y bar with all the other values which you could obtain by different separations. Now, if they actually come from different populations, differing in location, then the observed value of x bar minus y bar will tend to be one of the higher values. And from that, as you all know, we can get a test of significance. I merely wanted to explain how my mind arrived at that particular test. Except when the samples are, I wanted to explain the train of thought which started me off in writing a succession of 3 papers on what are now called non-parametric tests. I call this test the spread test. Except when the sample sizes are small, the labour of comparing the observed sample with the observed difference with all the other possible differences obtained by the different separations and finding how likely it is to be as large as it is if they come from the same population is quite heavy, the labour, unless the samples are quite small. I didn't think of greatly reducing the labour by replacing the observed numbers by their ranks. Had I done so, I'd have discovered the Wilcoxon test in 1937, because that is what this test becomes when you replace the numbers by their ranks. I did investigate an approximation to the distribution of x bar minus y bar squared. That is the distribution in the separation when they come from the same population, and the use of that approximation is exactly equivalent to the using the ordinary t-test with normal assumptions. So I was surprised when, having kicked the normal distribution out of the door, I found it fly in the window. There was some difficulty about getting a paper called The Estimation of Location and Scale Parameters of a Continuous Population of Any Given Form published. Wishart, who handled all these papers, first sent it to Biometrica, but it was refused on the grounds that it was too mathematical for that journal. He then tried the London Mathematical Society and was again unsuccessful. The editor thought that the paper was too controversial, and he did not want his journal to be cluttered up with correspondence about it. Sir Harold Jeffreys was then asked to sponsor it for the Royal Society, but he refused, saying that it was somewhat like a paper of Neyman's which he had recently been persuaded to sponsor, and which, one gathered, he was not enthusiastic about. Finally, it was saved from oblivion by the editor of Biometrica, who generously offered to publish it, since no one else would. All this may seem very strange to present-day statisticians. There is nothing controversial in the paper. It is all mathematics, which no one has ever faulted. It is written in perhaps a somewhat pedestrian style, mainly because I avoided the use of conditional distributions. This was partly because of doubts about my own knowledge of them at the time, but mainly because I feared that some of my readers might not fully understand an argument using conditional distributions, and so might doubt the validity of some of my conclusions. I wanted to be clear and uncontroversial and convincing. In this paper, I introduced the term estimator into statistics as the name for the function of the observations whose value is used as an estimate of an unknown parameter. And when I start to think about estimators, and I particularly started on location and scale parameters, I realized that there was no hope of getting any sensible results unless you somehow limited the class of estimators which you're studying, because always in the background there's the constant estimator, namely the value of the parameter whose value is the value of the parameter you're estimating, and is certainly the best estimator at that point. When you speak about all estimators, it's the same as all functions of the observations. Well, I thought now, considering location parameters, like when you've got a distribution with a density function f of x minus a relative to a measure mu, and relative to a vague measure, I should say, and you say, what sensible conditions can you require of your estimators? Well, the obvious one is what I've written here. If, when you observe x1, x2, xn, you would say that a is equal to a naught, then when you observe x1, x2 all increase by lambda, you ought to increase your estimate by lambda. In other words, your estimator, your A estimator, ought to have this property. You get similar things for the C estimator, the scale estimator, where you have a density C minus 1 f of x over C, and the scale parameter C greater than 0. In the same way, you show that you should have an estimator with this property, that C mu x1, etc., is mu times C x1, etc. And when you have to estimate both A and C, where you've got a density function of this form, then your A estimator ought to have this property, and the C estimator ought to have that property. When that is so, you have the fact that A minus A over C the C estimator over little c, and big A minus little a over c all have distributions which are independent of A and C. And in that paper, only estimators with those properties were investigated. I could not think of a suitable adjective to attach to them. They're now called, as you know, invariant estimators. I don't know whether anyone in practice uses any others. The doubts about the paper arose, I think, because I used the word fiducial. I use the term fiducial function as a name for a probability density function which appears in the analysis and which is closely related to the likelihood function. The corresponding probability distribution I call the fiducial distribution. But these are merely technical conveniences. It was necessary to give names to these things. I do not speak about fiducial probability except to say in one place that Fisher does. As R.A. Fisher expresses it, the fiducial probability of the variable statement 4 is alpha. The fiducial distribution in the AC plane, that's in the parameter space, isn't the probability distribution of the unknown parameters A and C. It's simply a probability, two-dimensional probability distribution from which confidence regions for A or for C or for A and C can be easily obtained. The last of the 8 papers was published in July 1939 issue of Biometrica. The Second World War started in September of that year. That put a stop to my flow of papers. At the beginning of the war, the mathematics staff of the university consisted of myself and Dr. J.C. Jager, a very able applied mathematician. He was very soon seconded to the Commonwealth Scientific and Industrial Research Organisation for war work. I had to do the best I could with a part-time assistant lecturer. Besides teaching mathematics, I had heavy administrative duties as I was chairman of the professorial board and a member of council, the governing body of the university. In addition to this, I took on the job, which was really a full-time one, of Honorary Education Officer for the Royal Australian Air Force in Tasmania, in charge of selection and pre-enlistment training of aircrew and responsible for determining and accepting or not the educational standards of all Tasmanian applicants for entry into the Air Force. Later, when the Air Training Corps for youths under enlistment age was started, I was Wing Training Officer for Tasmania. I had no time or energy for research. The war ended. I was able to get back to research, and Cramer's Mathematical Methods of Statistics was published, most opportunely for me. I was surprised and pleased when soon after the war, early in 1947, I was invited to visit Columbia University and the University of North Carolina and give courses in the theory of estimation and testing statistical hypotheses and in non-parametric methods. I was later invited to visit Princeton also. In January 1948, I sailed from Sydney with my wife and 3 children in the Marine Phoenix, a United States troop ship. We were setting off on a voyage of faith and hope. At that time, there was a dreadful housing shortage in the United States. Although we'd been trying for nearly a year and using every means we could think of, we had not succeeded in arranging for accommodation. It was a happy beginning when on the first day out from Australia we received a wireless message to say that a furnished house had been rented for us in New Canaan, Connecticut, about 50 miles from Columbia University, where I was to teach for a semester. It was an adventure for me also because I was completely inexperienced as a university visitor. Although I had taught mathematics for 25 years, I had never given a seminar, nor had I ever attended one. The staffs of Australian mathematics departments were too busy teaching to have time for seminars. There were too few mathematicians in any one department. There were no graduate schools. We had very few overseas visitors, and we did not visit other universities in Australia. We did not have an Australian Mathematical Society until 1956. The Statistical Society of Australia was founded in 1962. I never discussed statistical theory with anyone who was not one of my students, except for M.G. Kendall's comment in the first page of the first edition of his advanced book, where he simply mentions my name in talking about estimator. He adopts the term. I had never seen any printed comment on my work. Finally, I was recovering from a severe illness. 5 or 6 weeks before we were due to leave Australia, I was taken into hospital with a burst appendix. Fortunately, by that time, penicillin had come into use and was available in Tasmania, and so I survived. But for more than a year afterwards, I was subject to recurrent attacks of extreme fatigue when I could no longer think. This never occurred when I was lecturing, but I fear some people may have found me rather dumb at times outside the classroom. We eventually landed at San Francisco after a voyage which was pleasant, except that we were not allowed to go ashore at our first port, Auckland, because there was a polio epidemic there, and then we were not allowed ashore at any other port because the ship had called at Auckland. I soon started at Columbia, gave my 2 courses and went to the statistics seminars. I was impressed by the standard and frequency of the seminars and by the discussion, sometimes quite fierce, and also by the fact that the graduate students attended regularly. At times the seminars were beyond the comprehension of most of them, but I thought that they learned much by being constantly exposed to them. I took with me to America a paper ready for publication which contained the theorem, which I was rather proud of, that, I didn't want that one, if x and y are independent, and also you can get ax plus by independent, with the a, b, a dash, b dash all non-zero, then the x and y have normal distributions. I was a bit disappointed. The first seminar I went to was given by Loewe, who just arrived from France. During the course of his seminar, he used a result which followed from this result and asked if anyone knew it. I was the only person in the room who did. In the discussion that followed, someone said he thought the theorem had been published in a Russian journal. Loewe, and neither Loewe nor I ever published it, but it did appear sometime later, and I think in a Russian journal. Abraham Wald was head of the statistics department. I had studied many of his papers and learnt much from them. When I gave a seminar, he showed his mathematical power in the discussion afterwards. I realised that he had completely grasped what I had done. I admired him greatly, not only for his mathematical talent, but also for his great humility and kindness. After the summer vacation, I moved to the University of North Carolina in Chapel Hill, where I taught for 2 quarters. At both Columbia and Chapel Hill, after a course was finished, with the help of students, I produced a set of notes. The Chapel Hill notes on non-parametric inference became well known and much in demand. They were widely circulated and were frequently referred to in the literature. 12 years later, the Mathematical Centre in Amsterdam asked for permission to make copies for mathematicians and statisticians in Holland. Recently, I was presented with a retyped copy by Nicholas Fisher, who had been visiting Chapel Hill. It was not entirely my fault that the notes were not published in a more permanent and more accessible form. Shortly before I left the United States, I was visited by a representative of an American publisher who asked if I had any manuscripts. I said yes, and told him about the non-parametric notes, but he was not interested. They would make only a small book, and his firm was interested only in big books. Could I expand the manuscript? No, not much. No deal. 20 years later, a publisher wanted to print the notes, but I refused. I said they had done their work and were now out of date. The things in the notes that were most frequently referred to were the method of obtaining the asymptotic power of a consistent test and the notion of asymptotic relative efficiency. Non-parametric tests had proliferated, but no one seemed to know anything about the powers of most of them. We consider the hypothesis H0 that theta is equal to theta naught, and theta being a real parameter, and we want to test it against H1 theta greater than theta naught. And the test we use is reject if Tn is greater than Kn, where n is equal to the sample number and the probability that Tn is greater than Kn under theta naught is equal to alpha n, which tends to alpha as n tends to infinity. Now the power function will say beta n theta is equal to the probability of theta that Tn is greater than Kn. We say the test is consistent if beta n theta tend to 1 as n tend to infinity. That is to say, if the true value is theta greater than theta naught for theta greater than theta. If the true value of theta is greater than theta naught, then the probability of rejection will tend to 1. We say the test is consistent. Well, power functions are nearly always difficult to determine, and we have to be content with approximations. What happens when n gets large? Well, if theta is greater than theta naught, beta n theta, the thing we're interested in, tends to 1. So that if we're to get any other result, we will have to use not a fixed theta, but a sequence of values of theta, named theta n, getting nearer to theta naught as n tends to infinity. That is to say, we try to find a sequence theta n such that beta n theta n tends to I've forgotten what I've got. Tends to gamma, which is such that alpha is less than gamma is less than 1. We try to find a value of a sequence such that that is true. Well, there's a point about this that doesn't seem to be realized. Supposing you get the limit of this, you choose a suitable sequence, theta n, and you get the limit of this when n tends to infinity is gamma. Well, then that, after all, that only means that when n is large, this is approximately gamma. So that this is an approximation to the power function when n is large at that value of theta. So it does give you an approximation to the power functions. You've naturally got to make some assumptions. Well, we assume that for theta naught less than theta less than or equal to theta naught plus h, for some h greater than 0, A theta and Wn exist such that the theta naught distribution of Tn minus A theta naught over Wn and the theta n distribution of Tn minus A theta n over Wn both tend to a distribution, a continuous distribution with distribution function f. Well, of course, in many cases, this Wn is the standard deviation of Tn, and this is the A theta is simply the mean value of Tn, but it need not necessarily be so, and f is the normal distribution function. But those are the basic assumption that these things actually exist, so that the theta naught distribution of that and the theta n distribution of that tends to a distribution which has a continuous distribution f. Well, then the result that you get, there's one other assumption. We assume that A theta has a derivative at theta naught such that A dash theta naught is greater than 0. Well, you find for lambda greater than 0, the limit alpha. In other words, this is your theta n sequence, theta naught plus lambda Wn over A dash theta naught. Well, that that gives you then, that means then that when n is not too small, this is an approximation to the 1 minus fk minus lambda is an approximation to the power function for this value of theta. And it's often quite a good approximation, even for not very large values. Well, the next, that I regard as the important thing, being able to get any kind of approximation at all for the power function. The thing that most people know about is the asymptotic relative efficiency of tests, where you take two tests and you want to compare their relative efficiency. Efficiency is a term imported from engineering and physics. It should be used only in a situation where there's an input and an output, and where at least one of these can be measured. Here we have a measurable input, namely the number of observations, and a measurable output, the power of the test against a specified alternative. Now, if we have two tests of the same hypothesis at the same level alpha, and for the same power with respect to the same alternative, the first test requires a sample of N1 and the second a sample of N2. It's reasonable to define the relative efficiency of the second test with respect to the first as N1 over N2. And the limit of this, when N1 and N2 tend to infinity, if it exists, is the asymptotic relative efficiency, ARE. I was delighted when I discovered that the ARE of the Wilcoxon test, which I'd failed to invent, compared with the t-test for samples from the normal distribution, had an ARE of 3 over pi. After 2 quarters at Chapel Hill, I spent a few weeks at Princeton and then returned to Australia. My connection with agricultural field trials had ceased some years before the war. From time to time, I was consulted about statistical problems by members of the university staff and by people from the State Departments of Forestry and the Department of Health. But this work raised no problems of theory. There was so much to be done in statistics in those days that the problems put up to you were nearly always relatively simple. But it was in my teaching that I met such problems, to which I had with me for years before, and did eventually publish my solutions of, were about the relation between the behaviour of the distribution function in the neighbourhood of plus or minus infinity and the behaviour of its characteristic function in the neighbourhood of naught, and about the Cramér-Rao inequality. With regard to the first, it was the paucity of, one was always told, you always read, that the behaviour of the characteristic function in the neighbourhood of the origin depended upon the behaviour of the distribution function in the neighbourhood of infinity. But it not told very much about how they were connected. Well, suppose we've got a distribution function f and a characteristic function phi. For x greater than or equal to naught, put hx equal 1 minus fx. Tail sum and kx equal 1 minus fx minus difference. And u and v are the real and imaginary parts of the characteristic function phi of t for t real. Let's say phi t Now, we know that u depends only upon h, the tail sum. Those are the tails of the h is the sum of these tails and k is the difference. And v depends only upon k. Now, h and k are not very closely connected. The only connections really are that h is greater than or equal to the mod of kx, and hx plus or minus kx are both non-increasing functions. Those are the only connections. You can any functions for h and k as long as they obey those two. Since u is tied to h and v is tied to k, the important thing is then to consider them separately. That's to say, consider h and u and k and v. And I've spent a little time on that because it's such a simple thing, but makes the whole work a lot easier. Until then, all the results you had, the characteristic function h and k considered together and u and v considered together. But when you do that, the thing is very, very manageable. I stated these results at the fourth Berkeley meeting on probability, and published them sometime later. I first met Sir Ronald Fisher in 1953 when he came to Australia, his first visit. He came to Tasmania for a few days after Easter and stayed with us. We found him a charming guest. At a party you could lead him up to anyone or anyone to him, make the necessary introductions and explanations and leave them. He would quickly have the other person interested in talking with him. When I asked him what he would like to do when he visited the university, he said he liked talking individually with research students in a laboratory, and that he did not like to be asked to say a few words to a gathering. He surprised me, and I want this to be recorded because I think most people will be surprised from some of the things he said. He surprised me by saying that he thought that the greatest effect of statistics on the world was in quality control, because we had so many complicated things like aircraft with thousands of parts that without quality control their manufacture would be impossible. I visited Stanford University for 3 quarters in 1957. While there, I was conned into writing a review article on Fisher's statistical methods and scientific inference, which had just been published. I did not try to write an ordinary review which is intended to help a reader decide whether to buy the book, borrow it, or ignore it. I addressed myself to the people who had read the book, to those who would read it in the future, and to Fisher himself. He had spoken and I wanted to continue the scientific dialogue. He didn't like my criticism of some of his arguments, but as far as I know, he never attempted to reply, and he never raised the subject with me. Indeed, for some years, he could hardly bear to speak to me when we met from time to time in various places. However, we did eventually become friendly again without ever discussing the matter. The beginning of fiducial probability, fiducial distributions, and confidence intervals was Fisher's 1930 paper, Inverse Probability. The basic idea in his argument, we all know now, but it's worth looking at, is extremely simple, but no one seems to have thought of it before Fisher. Let T be an estimator of a real parameter theta. Define k theta by the probability that t is greater than or equal to k theta is equal to k. K being a number between 0 and 1, define k theta by the probability that t is greater than or equal to k theta is equal to k. Now, if k is an increasing function of theta, the inequality here is equivalent to k theta is less than or equal to k minus 1 t, where k minus 1 is the inverse function of k. So you therefore get the statement of that is equal to k. You can write that as probability theta. Now this, of course, apparently, as you know, is a statement on theta, and you have a definite probability of that statement being true is equal to k. Now, it's hardly possible for present-day students of statistics to appreciate the liberating effect of the mathematically trivial step, just reversing the inequality, a simple twisting of inequality. Neyman expressed himself as follows in the discussion: the possibility of solving the problems of statistical estimation independently from any knowledge of the a priori probability laws discovered by R.A. Fisher makes it superfluous to make any appeals to the Bayes theorem. The present solution means, I think, a revolution in the theory of statistics. When I read the paper, was enthusiastic. I remember the first time I talked about it in my lectures. The next time I met the class, I went up to one of the students. I said, "Where did we get to last time?" I looked at his notebook, and he had printed across the page in large letters, after his last letters, "better than Bayes." So he definitely got the message. Well, it hasn't turned out to be so quite so wonderful as we thought. At least, I don't think so. However, it is still a step I don't think we'll ever get very far in that direction, that we'll be able to do much more with this kind of statement than I did in my location and scale parameters, where I obtained corresponding statements for A and C, the location and scale parameters. The other, I was speaking before about problems that bothered me. The other second problem that bothered me for years was about the Crimea-Rao inequality. Well, you know it. Let me write it down for you. Mu is a measure on a probability space. F is a probability density that depends upon a real parameter theta and determines a probability measure p theta on the place. And S is a statistic with a finite variance. The mean value of S is equal to h theta, is a function of theta, and Vs is equal to the variance of S. You have, of course, integral f d mu is equal to 1, total probability of the space, and it's assumed always that you can differentiate that under the integral sign. That is to say, the derivative of that, the integral f dash d mu is equal to where the prime denotes differentiation with respect to beta. And you have h theta is equal to the integral s f d mu. And if you can differentiate that under the integral sign, you say the statistic is regular. And you know that when that's all true, you get the Crimea-Rao inequality at h dash theta squared over the variance of S is less than or equal to and we call that I. And of course, in the simple case, when h dash is equal to h theta is equal to theta, then you get 1 over the variance of S is less than or equal to I, which is the usual thing. Well, now R.A. Fisher seems to have been the first to encounter this expression. He called it first the intrinsic accuracy of the distribution, and later the amount of information in a sample, in an observation rather. The observation might be a sample. The first name is dropped out of use. It's now usually called the information or the Fisher information. More often the Fisher information, because people don't like to call it. That's to say, they usually use that merely as a name. Now, I think that's a bad practice, because it's misleading. I theta is equal to integral df by d theta squared over f d mu. Now supposing you take phi, a function of theta, that's not the parameter theta but some function of it, then I phi will equal to I theta over d phi by d theta squared. Just df by d phi is df by d phi by d theta multiplied by d theta by d phi, or divided by d phi by d theta, and the squaring brings it that way. Now supposing we take phi equals theta cubed. That gives you I of theta cubed is equal to I theta over 3 theta squared. And if we take I theta to the third, that will equal I theta over the derivative of theta to the third, that is 1/3 theta to the minus 2/3, which is equal to 3 times theta to the 2/3 I theta. Well, now supposing at theta equal naught, I theta is greater than naught and finite. Well, I of theta cubed, this is 0 equal infinity, and I of theta to the third, I of theta to the third is equal to 0. So that you have finite non-zero information about theta, infinite information about theta cubed, and 0 information about theta to the third. Obviously, you're dealing with a derivative, and it isn't information. You have I of theta is equal to the integral of f dash d mu. That is equal to 4 times the integral d by d theta of f to the half d mu. This is simply 4 times that derivative f to the half. You get a half in it. When it's squared, I want it squared. Squared. So you'll have I theta naught is equal to the integral of the limit theta tends to theta naught, 4 times that, of f to the half minus f naught to the half. F naught means the f function when theta is theta naught, squared d mu. Now, if the integral of the limit is the limit of the integral, let's say that is equal, perhaps, of 4 times the limit squared d mu. That is equal to 4 times the limit rho squared over... I've lost my theta minus theta naught, haven't I? What have I done? I'm sorry. Over theta minus theta naught squared. This is the limit of that, I forgot my denominator, is equal to 4 times the limit of theta tends to theta naught of that. That's equal to the limit theta tends to theta naught of rho squared where rho squared is equal to so that is what the integral f dash over f really means, providing that is true. Now this, of course, the rho here is the L2 norm of f a half minus f naught a half. It's a distance between these two functions, and it has all the properties of a distance, and so it's a distance really between the two probability measures. That distance is sometimes called the Hellinger distance. I don't think it's entitled to any special name, because if you're dealing with probability densities, you're dealing with non-negative functions which are integrable, and therefore their square roots, which are real, are square integrable, so that they're in L2. Well, L2 is the analyst's heaven, and he always desires to get there, so it's the natural distance to use for distance between probability measures and the distance between the corresponding densities. Well, I said that when this is true, that's to say when I is actually the limit of that, the limit of that, I've said that the family of probability measures is smooth. Well, it turns out that the Crimea inequality is of interest only when the family is smooth. And then, which statistics are regular? Well, it turns out that any statistic, if the family is smooth, any statistic which has a variance bounded in some neighbourhood of theta naught is regular. So you can't have anything much simpler than that. And I say you'll find it's only of interest when the family is smooth. And when the family is smooth, you've got that simple criterion for regularity. Now, in conclusion, I wish to say that I take the view that the aim of the theory of statistical inference is to provide a statistician to assess the strength of the evidence supplied by a trial or experiment for or against a hypothesis, or to assess the reliability of an estimate derived from the result of such a trial or experiment. In making such an assessment, we may look at the results to be assessed from various points of view and express ourselves in various ways. For example, we may think and speak in terms of repeated trials, as for confidence limits, or for significance tests, or we may consider the effect of various loss functions. Standard errors do give us some comprehension of reliability, but we may sometimes prefer to think in terms of prior and posterior distributions, or to consider a fiducial distribution. All of these may be helpful, and none should be interdicted. The theory of inference is persuasive rather than coercive. It does not provide a set of infallible rules which are to be applied automatically. If the theory of inference is to be of use to the practicing statistician, it must be clear and simple, and much statistical theory isn't. Regularity conditions of all theoretical results are often flung down with scant regard for the possible user. They're often too strong, and they're often difficult to verify in actual cases. In the development of a theory, simplicity usually comes last, but we must continually strive for it. Finally, I want to stress the necessity to be honest. We must be scrupulous in the use of terminology so as not to mislead by suggesting more than can be justified. We must avoid the indiscriminate use of terms like efficiency, information, and best.